All right, so the second fundamental theorem, we need to make sure we understand how to find the derivative of integral defined functions. It is the easiest of the derivative rules. I think sometimes students make it out to be much harder. It is essentially the derivative rule that is like if we had it, the same as like multiplication, division, antiderivative, derivative are going to reverse themselves. It'd be like if I said, what is 126 times 18 divided by 18? You'd say it's 126. You don't actually have to do the multiplication and division in that problem. Same thing here, right? This is telling us do the antiderivative. When we do h prime, it's asking us to do the derivative. So they are reversing themselves completely. And so it's going to be h prime of x is just going to equal x squared f of 2x. So we took the antiderivative, plugged in x, and then took the derivative, and it came right back to where it was. We realized we don't have a derivative rule for actually doing this in AP calculus. In BC calculus, we would do an integration by parts, but we don't have that in AP calculus. So we're not actually going to end up taking this antiderivative. But you can actually find it here. There's no chain rule in this. The chain rule is going to end up being in the bound if we have something like that. And you'll see that in the second question. All right, so in the second question, if we're going to find the derivative, h prime of x, realize that we take the derivative of the other terms just like normal, right? So this is just 4x cubed plus, now when we take the derivative of this integral, it's going to end up being this x squared is going to replace the t just like it did in here. So replace the dummy variable. This t is really a placeholder for that x squared. So it's going to end up being cosine of 5x squared, but this has a chain rule. So our chain rule, our inside function is going to be in the bound because we take the antiderivative of what's in the integrand, and the derivative is going to reverse everything in the integrand completely. But this x squared got plugged in as an inside function between those steps. So we're going to have to take the derivative of the inside function of just the what's in the upper bound. And so it's going to end up being times 2x is what is going to end up being our derivative for this. Don't put 10x, okay? Because this 5, when we do the antiderivative and derivative, that 5 inside function actually gets reversed through the second fundamental theorem, okay? Look at this one. We've never had a question like that. And that's something you're going to see like on the AP exam, is you're going to see questions where it's like, man, we've never done that before. There's no way I can predict all the millions of ways they're going to ask you a bunch of questions. But what we have to know is we know how to do this, right? If we had two other functions put together like this, what is this telling us we're going to have to do? Product rule. We know we have to do the product rule. We know the second fundamental theorem for how we get the derivative of this integral defined function. Right? And so what we're going to do is we're going to take the derivative. And so our product rule tells us we're going to take the derivative of the first, which is going to be g prime of x, times the second, which is all of this, unchanged, plus the derivative of the second. What's the derivative of the second going to be? That's going to be a little bit tricky. Negative f of x, yeah, because this is in the lower bound. So we did the antiderivative, plug in the upper bound, minus plug in the lower bound, and then took the derivative. So added an extra negative because our variable is in the lower bound. The other way you could think about it is we could switch these, get the x in the upper bound, and it would make it the opposite, right? That would add a negative. So it's going to be negative f of x, so plus negative f of x times g of x. And so who knows how this problem might be asked? You might be given a table, you might be given a graph, who knows? And you would be able to evaluate something like this, okay? Any questions over that? All right, let's take a look at these derivative rules. So I had a lot of people try to do this question on one of the practice FRQs as if this was f of x, x cubed plus x, and they did a product rule. And that is not what's happening right here. This right here is the inside function. So this is not what this is asking. So we need to do a product rule, a chain rule. And so we're going to say it's going to be f prime of x cubed plus x times the derivative of the inside function, which is going to be 3x squared plus 1. These parentheses are very important, okay? For those of you that just think parentheses are optional, it's going to be counted wrong. So you have to make sure it's times that derivative, the inside function. But f has the easiest derivative rule there is, right? It's just f prime, right? Now, in this case, in part question B, there is a product rule, right? So we're going to have to take the derivative of the first. So our rule for natural log is 1 over our argument. And then the chain rule is times the derivative of that inside function. So times 2x, and then times the second function, plus the derivative of the second function, times 2, times the natural log of x squared. And so this question, it's kind of tough, because you've got your derivative of your first times your second plus the derivative of the second times the first. So you have your product rule right there. But in each one of those derivatives, you had to do the chain rule. Okay, so you have to make sure you're aware of those inside functions. Questions over that? And you could simplify this in various ways. It might actually simplify to 2 over x g of 2x plus 2 g prime of 2x natural log of x squared, something like that, or there might be various ways you could do that one. All right, what about C? What are we going to do on that one? Quotient rule, right? So we're using the quotient rule on this question. And so the quotient rule tells us we take the derivative of the numerator, e to the 5x, times 5 times the denominator, minus your derivative of the denominator, which is going to end up being cosine of 2x times 2 e to the 5x, all divided by the denominator squared. Okay, so your derivative of the numerator times the denominator minus the derivative of the denominator times the numerator, all divided by the denominator squared.
Will the denominator be negative 2 cosine? So plus 2 cosine?
No, because the derivative of sine is positive. So there's a negative from the quotient rule, but the derivative of sine is positive. You're thinking antiderivative.
Oh, yeah.
Right? So make sure, and if you're thinking about it, you're not sure, there's that little way you can, I don't know if we talked about this, you can put like sine. So you put in sine was kind of like the y on the unit circle. So we had sine, cosine, negative sine, negative cosine. If you think about, clockwise being like your derivative, that's going to be your derivative values, right? Sine goes to cosine. So clockwise, and then think about antiderivative, like so counterclockwise would be the reverse way, right? And so if you're thinking counterclockwise, that would be like antiderivative, and so that would go the opposite way, okay? And so that's kind of, if you're not sure which way we're going, think about that. You have derivative, and then antiderivative would be like counterclockwise, right? So we're going to keep that in mind. All right, this one, we didn't do this one in class much. I do want to point it out because it could appear. There's a small chance it will appear. Usually they don't put it with anything else. And if you have to find the derivative of 3 to the x, it is just natural log of 3 times 3 to the x. That's it. And this is kind of why e to the x works out real nice, because natural log of e is 1, and so it goes away. You don't have this here. But on any other base, if we had to find 5 to the x, it would be natural log of 5 times 5 to the x. What you do not want to do is try to use the power rule where you multiply, and I see students say the answer is like x 3 to the x minus 1. That works for polynomials. It does not work for exponential functions. So you have to do this, okay? Another one you might see, they put it every so often, an inverse function. They're really hard. Nobody gets them right, but I'm just going to tell you real quick, just in case you have some inspiration on the AP exam or you have some time. If they give you an inverse question, they're using this idea that the definition of inverses is their composite function equals x. And if they're asking for the derivative of something, it's just f prime of g of x, use your chain rule, times g prime of x equals 1. And then you can solve for whatever's oftentimes asking for, like, what is g of 5? And you'd be able to find that like g prime of x equals 1 over f prime of g of x. And so if you get a question that asks you for inverses, this is the relationship you have to find the derivative of. Okay, so just realize that. The other thing about inverses, when you have an inverse function, you may remember from algebra 2, that the x and the y switch places. So if you have f of 6 equals 2, that means g of 2 equals 6. Sometimes you have to use that piece of information on there. Don't worry, if you get an inverse question, everybody misses them. They score, you know, sometimes when you look at the scoring guidelines, it's like they score close to guessing at random. So don't worry so much if you don't know that one. But if you have some inspiration, maybe you'll remember that's the definition of inverse, and that's the relationship that you take the derivative of. Same thing with this one. Maybe you'll remember that as well, right in there. We didn't really do those much this year because I think they don't show up very much. And it's not a huge part of the big part of calculus. On this one, you will have to know this one. They do like to ask you a lot of questions involving this, whether it's on the multiple choice or on the free response. You have to know that g prime of x equals what? F of x, right? And so oftentimes they're going to give you something, they're going to ask you a bunch of things about g on this integral defined function. They'll give you a graph of f, and you have to recognize that that f graph is the g prime graph. And so then you can use all the things we know about g prime. Another thing that happens is you sometimes get differential equations that look like this, where you have this dB dt is 1 over 3b. This could be, you know, the number of, the rate of change of, I don't know, bats that live in a colony or something like that. Whatever it is, who knows, right? It could be bats per time, right? And if you're going to actually find the second derivative of this, so d squared b over dt squared, we have to take the derivative of this, right? And so the derivative of this is really, this is going to end up being 1/3 b to the negative first. And so if we find the derivative of this, we get this negative 1/3 b to the negative second. And a lot of students leave it right there. But what do we need on this? What do we need to multiply by? dB dt, right? So we need to multiply by dB dt. And so we're really going to end up with negative 1 over 3b squared times 1 over 3b, right? So this would actually end up being your second derivative, okay? And so don't forget about that. If this was 1 over 3t, then it would just be, you know, negative 1/3 t to the negative second. That would be it, right? But we're taking the derivative with respect to time. So your derivative of b is dB dt. Is that, this is b prime. B prime is this dB dt. And so we got to make sure we multiply and do our chain. Okay? Any questions over that?
Could you simplify the last part to be negative 1 over 3b cubed?
9b cubed.
Oh, yeah.
Yeah, that's right.